As you see, we will start a new chapter, guys. This is about different types of curves, Hermite, Bezier, B-Spline curves. We will also discuss nerves types of curves in this chapter. And we will start always with a brief introduction. Why do we need to have such special curves? What are their application areas? We will go through them first and then start discussing one by one, and then we will have some relations between these types of curves. So what is spline first? Splines are actually kind of polynomials, and they have a fixed degree of polynomial. And another important property of splines is that they should be continuously differentiable. So we can easily take derivatives of these polynomials. And depending on the order of the polynomials, that obviously the number of differentiations can change. And as you see, they are differentiable up to some order. If you have smaller orders, you have smoother, let's say, curves. If you increase the order of your spline, you'll have some sharp, let's say, movements, but you may be satisfying some of the constraints. So where do we use such constraints? We use them obviously in covariate design to design such planes, such kind of parts, spaces, such surfaces. We need to make use of splines to make it as smooth as possible. You can also use it for toolpath generation for CNC machining or additive manufacturing. We do sometimes use it for motion planning of some kind of robots, industrial or some agricultural, let's say, or autonomous robots, autonomous cars. You can further use it for computer graphics, and this is one of the most common usage areas. We try to represent the objects by using splines. And for also graphical purposes, for visualization of data, you may again use the splines. You may fit a spline to a data and comment on the behavior of your data. And these days, actually, the main problem is you are given a set of data and you're trying to find a spline which is fitting into all of your data. It might be an interpolating spline or an approximating spline. We will discuss all these, but the main research is actually in this field is to find a better way to have the, let's say, kind of a spline fitting your problem with less errors. We may have parametric splines, which means that we are using vectors of a polynomial, actually polynomial functions, or we may have implicit splines, as the name implies. In that type of splines, you don't have a kind of a mathematical description of the spline, but instead you have a relation between the original one and the implicit splines. For instance, the contours of a polynomial, let's say you have such a contour, and you may simply say that you need to have a spline having an offset of, let's say, 5 millimeters to this curve. So if that's your definition, then that will be an implicit spline. Since you're not defining any function, any leaf function, you're not discussing the order of it. So that's why it's an implicit one. But for parametric ones, we need to have some numbers, variables, and with the help of them, we can represent these splines. And the splines are actually differentiated according to their type of representation, whether they are implicit or parametric, whether they are algebraic or have geometry degree to their spline bases, according to their patches, if they are a kind of surface, and according to their computation times and memory requirements, according to the stability of their fitting algorithms. Some interpolations they may have, some may not have. So they have many properties. You will see that some of the splines satisfy one of these and the other ones may not support it. And the type of input is also important. You may start with a mesh, or you may start with just simple control points, as it depends on the type of spline, curve, or surface you are working on. And convexity is another important issue. If your set of inputs is convex, then things will be much easier. So let's go into some details and how we started working on the splines. So things actually started with a flexible metal piece. They had a kind of a, let's say, a sheet metal, and it's a strip of flexible metal. And then what they do, they actually had some packs and attached some weights to this sheet metals, such flexible metals, so that they will have a kind of a smooth shape. And with the help of these control points, like packs, they obtained smooth shapes. As you see, this is actually the red one is flexible metal, and these are our packs. You can say that it's kind of control points. So you see our flexible metal is going through this point, and then another pack moving around it, and then going through the bottom one to the last one. So if you place your control points like it and your sheet metal, then that will be the curve you're gonna have. So in summary, by adjusting the position of these packs, you can obtain smoother surfaces for your flexible metal. So how do we satisfy the smoothness? In the drafting, actually, you should try to actually minimize the curvature. So if your curvature is minimized here, then that means you're gonna have smoother spline. But in computer graphics, if it's a computer graphics spline, this is computer graphics, then we need to actually have this smoothness due to the function, due to the basis functions we are using. You cannot obviously do it by the flexible metal or the packs, since this is done in the computer. You need to make use of smoother functions. And this is mostly done with the help of low-order polynomials, usually second or third order polynomials. Let's say if you have 8th-order polynomial, then most probably you have such kind of things, and this is not smooth as you see. And furthermore, how do we control the shape of this splines? And obviously in the physical experiment, physical case, by simply moving these fixed packs, you can obtain various shapes, various splines. But in the computer graphics side, we have an analogy between that, and we make use of control points. Assume that these are control points, you may have such a curve. This is some kind of a spline, and we control this computer graphics spline with the help of the control points, and these are the control points. Any questions, guys, we have before we go on? No questions? Okay. And now let's start discussing some details. We will have parametric curves, not just a single curve. A single curve may not be enough to satisfy your, let's say, requirements. Assume that this is a third order curve, and that may not be enough to represent your data. So what do? You have some parametric representations, and you may join two curves together or many of them together. Assume that this is the second portion, and these all will be represented with parameters. You may be using actually the same function, but it may be valid between different regions. Now assume that in this case, and this is our whole spline, and we define our spline with a parameter t. And this parameter is in between 0 and n, and this f of t function might be a piecewise polynomial. So you will have some discrete regions, depending on some other parameters, that might be your piecewise polynomials. Here you see, for instance, two different types of spline. In the first one, we have, I think, an order of about 3, and this one is an order. What is the order of the low one? This is probably third order. What is the order of this one? Okay, guys, what is the order of the below line? The below one. It's just a straight line. Yes, it's a first order line, first order polynomial. Okay. So obviously, if you have piecewise polynomials, then we will have discontinuities at these intersection or at these connection points, and you need to be careful about it. If your application require, let's say, at least some differentiability at these intersection or connection points, and you need to increase the order and satisfy some constraints. For instance, if you look at a cubic spline, which is valid between some parameters k and k plus 1, this might be such a region. And if that's the case, k will be 1 and k plus 2 is obviously 2, or it might be between 2 and 3. So these parametric representations will be valid for these specific regions. But the thing is that they may have different coefficients. Depending on the coefficients, that's why they have some orientations, or their directions are a bit different. You see, this is a third order parametric representation. And we have here obviously t to 0, and x values, x coordinates are represented again with the help of t, and y is the same. So for instance, if t is equal to 0, then what will be the x of t? It will be simply equal to dx, right? And again, for y of t, it will be equal to dy for, let's say, the maximum value t1, t is equal to 1. And in that case, our x of t will be equal to, let's say, the summation of some numbers, okay? And again, y of t will be the same. T is 1, so it will be equal to ay, by, cy, and dy. So this is how we are going to compute all these points. So if you want to determine a specific point here, then you should do it by giving the appropriate t value and obtain the exact coordinates of all these intermediate points. So that's why we call it as a parametric representation. This is our parameter t, and with the help of it, we can represent the splines. And obviously, we may have different coefficients for each interval. Now let's focus on some coordinate functions. Assume that this is our spline. And now we are going to represent it with just x coordinates and y coordinates. So this is the x coordinate function. And it's just representing the x values. So if you look at here, I try to draw it. And if you increase, let's say, t from 0 to some value 2 here, so that means we have divided this part into 2 regions, then probably we have kind of a value here, right? This is the start of our curve. So intermediate points. and the end point. So at t is equal to 2, you should have such an x value, and at t is equal to 1, that is our value, okay? This is the x coordinate function, and we are only considering the x values. And this, we have the same one for the y coordinate. Again, this is our intermediate point, always the starting point and end points. So once you have these parametric representations of your coordinate functions, then you can determine these values easily. Any questions, guys, about the coordinate functions, parametric representations? Okay, how we are now going to control these splines? We have the representation, but how the control is done is simply done with the help of control points. Or sometimes we call them as vectors. If you have a different representation, then you may say that the spline can also be controlled with the help of the vectors. But for most of the splines, we prefer to use control points. So with the help of these, we are actually guiding our shape by simply moving these control points to each other, or we make them away from each other. And we may have an interpolating type of splines or approximating type of splines. In the interpolating type, you will see some examples that the resulting spline should be going through the control points. So if that is your control point, then, and if it's an interpolating spline, then your spline should be moving to your control points. But if it's an approximating one, then that might be going through away from your control point. Since it doesn't have to actually go through the control points, this is an approximating version, so it just approximates your control points. This is the main difference. So now let's have a look at some examples. These are the control points, and as you see, we have 6 of them. So what do you think? What type of a line, a spline is this? What is the order and what is the type of this spline? Whether it's an interpolating or an approximating spline. Come on, guys. So tell me the answer. No. Okay, then I'm skipping all these. Then let's switch to here. This is all discussed, so I don't need to discuss it. So what are we going to do in the rest of this chapter? We will talk about some other spline segments, spline curves, and to the end of the chapter, we will discuss the NURBS, non-uniform rational B-splines, and finally, we'll go through briefly about the offset curves. So this is the thing I'm not going to discuss since we didn't mention anything. So let's focus on the more complicated ones. So in the linear version, we will always have 2 points, as you see, P1 and P0. And then we can represent this function, this linear function in the matrix formulation like this. This is our parameter T. And by using such a multiplication, we can represent this baseline, let's say, spline, piecewise spline. And this is our control points, starting and end points. So we can do the formulation in a different way, actually. We can do the grouping by using T instead of the control points. So here, as you see, the same function is represented And this is a parametric function depending on t. And now the right-hand side is also grouped according to the order of t. That is order t0. Okay. This is the representation with respect to the points. And if you look at the matrix representation, matrix viewpoints, so if you consider this multiplication, you can do this multiplication and try to decrease the size of it to 2 by 2, and that will be not 2 by 2 actually, 1 by 2. And if you multiply with the coordinates, the control points here, you will obtain the final parametric representation. So now what we are going to do, we will have a kind of blending formulation. So we have the points, and sometimes you may simply take the average of points, which is the easiest one. You may just have half of one point, half of another point, and then obtain the intermediate point. But instead, to make it more complicated, to have various types of, let's say, splines, what we do, we use some blending functions. So they are not just the average of the points, but we have some parameters, some coefficients. So the thing is that the contribution of, if you use blending functions, then the contribution of each point will be modified as you change the parameter t. So they will not be the same throughout the whole region. It will be modified according to the coefficients, according to the function, according to the blending function you are using. So here you see, for instance, two blending functions, B0 and B1. Now we will be using these blending functions to represent the simple spline. Any questions, guys, up to now? Okay, now I'm going to start discussing the types of spline, and this is the Hermite splines is the first example, and it's one of the pretty trivial examples. And after we discuss this one, we can switch to the Bezier splines, which are a bit more complicated than this one, and then further we'll go on with some more complicated splines. So here you see a kind of a third order, a cubic piecewise spline, a piecewise cubic spline. This is our starting point, and this is our end point, P0 and P1. And in order to define this cubic spline, we need to have, in addition to the P0 and P1, we need to have some tangent vectors. You can also consider them as derivatives, but these are the constraints you should give. Otherwise, you cannot draw a piecewise cubic spline. These are the requirements, and these should be given. So what do you think? Can we draw just a single spline between these 2 points, or many of them? Assume that this is P0 and P1. What happens if we don't have the tangents? So I may have such a spline, have another one, or have this, not possible, but you may have such a kind of a curve, maybe this one. So as you see, if you do not provide the tangents, then you will have infinite number of possibilities. But once you define the tangents, then you don't have much option. You can only have just a single solution. So here you see, for instance, in this example, we have the same start and end points. They're horizontal, but the difference is that their tangents are in different orientation, in different directions. You see, by using the same control points, and we are only changing the directions, the derivatives, and we obtain various curves, and they are all cubic. Any questions, guys? Okay, So now how we are going to represent this Hermite splines in a parametric way? What we are going to do, we will be solving our problem by using the constraints. Since we have constraints, then our coefficients should satisfy the given constraints. What are they? First of all, if you remember, we have two starting points, endpoints, starting and end point. And then we have two derivatives, or the tangents. So we also need to have an equation for the derivative function. We simply take the derivative of x of t here, and then we can now use the constraints. For the starting points, here t is equal to 0, since this is a starting point. And once you put 0 for t, you will obtain that x0 is equal to d. This is our starting point. And we can also do it for, again, tangent vector, the starting tangent vector. And if you do it, then our tangent vector will be equal to the parameter c. And then now let's have a look at t is equal to 1 case, which is the endpoint. And if you simply put 1 into our equation, parameter equation, you will obtain that the summation is equal to x1, which is the endpoint of our parametric spline. And then we do the same for the tangent vector. Again, our parameter right now is equal to 1. And if you simply put 1 here, you will see that our final tangent vector, or the tangent vector at the endpoint, is equal to 3a plus 2b plus c. So now we can simply use this, use these four equations to obtain the relation between the x1, x1, x0, x1, and their primes and the t. So we can represent these coefficients in terms of the given variables, given inputs. These are starting endpoints and tangent vectors, or derivatives. So instead of using the coefficients a, b, c, and d, we can use these expressions so that it will be easier for us to represent them with the help of inputs. This is a fundamental thing. Now we have a bit different formulation. So this was our initial formulation. We have coefficients a, b, c, and d. But in the previous slide, we obtained an expression of these coefficients in terms of the given inputs, right? And these will be in the matrix representation. This is our kind of inputs, or the things we can control actually. Starting points, endpoints, and these are the tangent vectors. This is tangent at x equal to x0 point, and the other one is the tangent at x1, or tangent at the endpoint. And we have our parameter set. This is a cubic function, so we need to start from the third order, second one, and 0th order. Now we don't know actually. We can calculate calculate since we know this values here. The coefficients are represented with inputs, so we can complete these matrix, and that will be a nice way of representing the curve, since it will be valid for the whole, let's say, regions in our complicated spline. So as we said, that is, you can represent the whole spline into some smaller patches, and in all these smaller patches we will be using the same basis functions. These are Hermite basis functions. So the only thing is that if you know the starting point, end point, and their tangents, then simply by multiplying these input values with the blending functions, or the Hermite functions, or Hermite basis functions, you can obtain the final representation of your curve. So if that's the case, for instance, this is P0, and this is P1, and we have a kind of a vector here. This is T0, and we have another vector here, like this one, and that is T1. So if you have information of these, then if you later multiply the given inputs with the blending functions, you will obtain the representation of this cubic Hermite spline. Any questions, guys, up to this point? How we obtain the basis functions? So basis functions are actually the columns. The columns here, this is, for instance, E2. And the rows are actually the coefficients. The coefficients we defined in the previous slide here. So obviously the matrix form is much simpler, and you can see now the values are written into the matrix. And we know that the coefficients are represented in the rows, and the basis functions are represented in the columns. So you can simply, for instance, draw the basis functions. Let's have a look at this one, this basis function. B0 of t, what is that? It's 2 times t to the cube minus 3t squared plus 1. So this is our first blending function, or first, let's say, Hermite basis function. Let me write the other one. For instance, B3 here. That is t to the cube minus t squared. So these are our basis functions, and if you simply multiply these functions with the points and the tangent vectors, you will obtain the final representation of your spline. And you can do it for x and y separately, or you can just represent them in a vector form. Questions, guys? Okay, these are the representation of the curves, for instance, and they prefer to use, instead of writing, let's say, B3, they use for the Hermite H11, and this is B0, and you can check it. For instance, this one is here, and this is t to the cube minus t squared. And as you see, they are valid between 0 and 1. And for different type of functions, for different type of, let's say, splines, we will have various basis functions. If it's a Bezier spline, then we will have 4 different basis functions, but the fundamental idea is the same. Once you have these blending functions, then simply multiplication of these will give you the resulting spline. So let's have a look at the transition. Now, up to now, we discussed the Bezier curves. Now we'll switch to the, we discussed Hermite curves. We will switch to the Bezier curves by using the fundamentals of Hermite. In Hermite, we have 2 points and 2 vectors, right? But it's quite weird. Why do we have vectors and points at the same time? Why don't we just have points to represent the splines? But what happens if you just have control points instead of some control points and some control vectors? That will be much easier. So now we are going to represent these tangents by using some extra points. And these extra points will be around here, for instance. And as you see, this is the original tangent vector T0, and this is the reverse of the original tangent vector. Initially, if you remember, that should be in this direction. This is T1, but we reverse it simply, and now you'll see that we will multiply the difference between them by 3 to obtain the coordinates of these. Now, this is actually our new control points. Instead of using tangent vectors, we will be now using 4 control points. And in order to make a smooth transition between Hermite and Bezier splines, we use different terms for the control points of the Bezier. You see we have Q0, Q1, Q2, and Q3. You can easily see that P1 and Q0 are equal to each other, and on the other hand, P1 and Q3 are equal to each other, but we need to define Q1 and Q2. So how we do that? We have this relationship, and this comes from actually some basis functions. We are not going to discuss the details, but we can take it as granted that there is a relation between the tangent vectors and the points such that the difference of them multiplied by 3 will give us a tangent vector, and it's also the same for the end tangent vector.